Hi everybody, this is Tom from my rabbit hole. I want to share progress on the changes to my hobbing machine spindle and the addition of a Spur gear differential. I hope you enjoy it. This is the layout for the Spur gear differential that I'm working on. The whole thing is only about 6 inches in diameter. Basically, there's two 40-tooth gears in a stack here. You can see those right there. And then there's four 20-tooth gears that form the differential part. These gears mesh with each other, but each of these gears only meshes with one of the two 40-tooth gears. This is not an uncommon differential setup. I'm kind of sorry I didn't think about this before. I think it might have made some of my other stuff a little easier. So basically there'll be a hub and a plate, and another hub and a plate. Each one of those hubs will carry a back-to-back pair of angular contact ball bearings, ABEX 7 bearings. This one here will be larger. It's not drawn that way, but it's going to be like a 2.5-inch gear or bearing. And these are going to be smaller here. These just carry the input shaft. This will ride on the shaft, ride on the old input shaft, and there'll be a new input shaft here that carries the flywheel and the input from the index train. I am here today to talk about the assembly of my Spur gear differential, which is going to replace the bevel gear differential that I lovingly screwed up by putting it inside my spindle assembly. It's all part of life's learning process. So I'm going to show you this. We're going to put it together, and then we'll install it on the spindle in a later video. Part of the reason which is I kind of cleverly made this almost but not quite unassemblable on the actual machine. So I'm going to have to do a little more fiddling, but I'll show you what it looks like when we get it all together. So the way this is set up, there are two housing flanges. This one goes around the input shaft. This one goes around the output shaft. And we'll start by putting that together. These are ABEX 7 precision bearings. These come from China, actually. They're Mochu brand. They're available through Amazon. And I have to say, they're pretty doggone good for the price. I mean, these bearings here are probably about $22 or $3 a piece, which is more than the cheap bearings that they sell. But these things are incredibly precise and smooth, and I'm a big fan. If you bought from SKF or one of the European brands, you'd be paying probably $600 or $700 per bearing for these things. Now you might be able to tell the difference, but I can't. So anyway, these are going to slip down into that bore, slip down into that snugly fitting hand press bore. With the arrows pointed outward, that tips the angle of contact toward the outside. Let's see if I can do this. The contact angle of the bearing should go like this. You want the spread on the shaft side rather than on the support side. Now I think we can put this shaft in now, and the nut, which has got the O-ring
carried, or the oil seal, double lip oil seal is carried on the outer part there. Took me a couple of tries to get that nut design right. But I wanted to get a complete oil seal system. You'll see how the other pieces of that work, but there's a shaft seal on the other side. There'll be RTV between the steel plates on the outside and the aluminum ring on the inside. So now we can put the input gear, which gets a spacer, and a slip fit pin that serves as a keyway, or a key. I don't know if you can see that. Anyway, that slips in after you put the thing on. And then this gear slips over that key. I like working in brass, you know. There's something about the look of brass mated with steel. Dang, I don't know what it is, but it really does it for me. Now, two of these things get spacers and a gear, and two of them get gears and a spacer. I don't know how important it is that they be the same diametrically opposite. It just seems to make sense from a mechanical standpoint. And then we're ready to put the ring on. When I'm doing final assembly, this will all get sealed off. Now we can put bearings in the other side. Again, the arrows need to point out, which I believe these do. I don't know if you can see those arrows there, but the higher class bearings, these are ABEX 7 bearings, all have that kind of marking on them. And I have to say, I didn't really appreciate the difference between these precision bearings and the standard run-of-the-mill cheap ball bearings that you can buy on Amazon. But these things are actually pretty impressive. I mean, they are just beautiful. They feel good, they look good, but the ones I've bought don't have oil seals on them, so I have to put an external seal and provide at least some minimal level of lubrication. In my case, I'm just going to put 30 weight oil in the. These are really nice fit. I guess all my mistakes canceled out or something. You guys know how the fast forward thing works, right? I don't have to explain that, I'm pretty sure. While I'm struggling. Oh, there we go. This nut carries another seal, like the one on the other side. And we'll put the shaft in a minute. that's tight enough for this demonstration. Now, I think we can put this in. Wait a minute, that's going the wrong way. Again, getting the fit just right on these bearings is not always the easiest thing to do. There we go. That's in all the way. Oh, there we go. That felt like it hit bottom. You can put the bearing spindle on the outside, or the bearing thing on the outside, the shaft support, and then it's got grease on it because I was just test fitting it. This one's got a spacer ring and a little short key. Now this is probably the fiddliest part of this whole thing, which is getting this on in the right way. And I put alignment marks on the housings to do this. Well, I think it's meshed. On. Uh-oh. Crap. Sigh. This is the input gear that goes on the on the drum of the differential. So the signal from the lead compensation train comes in through this 90-tooth gear. Okay, let's try that again. Okay, key, the gear. Okay, now all we should have to do is put these screws in. Yeah, phooey. Feels like it's not quite. Oh, there we go. Still turns, that's a good sign. And that's it. So that's what the, I suppose you could call it a pancake differential, a spur gear differential. This design used to be fairly common, I guess, in some of the early automobiles. Just because, for the same reason I made it, it's relatively easy to make. You don't have to fuss with it too much to get a decent differential. It's a pretty good differential for a machine tool. I think overall, the bevel gear design is more compact from a diameter standpoint. This is a 6 inches diameter on the outside, about 2.5 inches thick in functional sense. Then this goes in right where the worm drive for the input, that used to be the input, goes, and the U-joint for the index train goes here. And then I have to make a couple of changes to the side plate on the spindle housing to provide the gear input from the other side for the lead compensation. But this works pretty good. It feels good. It doesn't have any catches or tight spots. It's not bad. Not bad. Well, this is a kind of a trial layout of the lead compensation train. This is the differential shaft, and that drives the 40-to-1 worm gear. This is the lead compensation shaft that used to be the lead compensation worm drive, but I've taken the worm out and replaced that with a screw there to preload the bearings on this side. And I've added a little half shaft here that will be attached to this shaft by a drive pin or maybe a slip pin there arrangement, and it's loaded against this class 6 sealed bearing here that will kind of be an outboard bearing for this bearing support system here. And then that goes through a 30-tooth gear here through an idler to the 90-tooth gear that's on the back of the differential. And this is the rear plate of the spindle assembly, and this is the front plate here. So this kind of spans across the space, and then the drive gear for the for the spindle goes here. This setup will give me a 3-to-1 ratio between the lead compensation train and the drum side of the differential, and then I add that, or I multiply that by the 40-to-1 that's embedded in the worm and gear combination there, and I end up with a total embedded ratio, machine constant of 120-to-1, which is what I wanted for the lead compensation system. That keeps the change gear ratio manipulation reasonable. I have a reasonable range of change gear ratios to deal with. So anyway, that was my target lead compensation ratio, and it looks like that's going to work pretty well. This is a tiny bit half-assed here. I just didn't want to make a new shaft. So I'm trying this setup here with a slip fit probably. Good support on this end, good kind of outrigger support on this end. And I have to make a bearing support. It'll be something like this that goes on this end. And with that and the modification to the housing, and I'll have to do something to support this idler, this job is getting very close to done, and pretty soon I'll be able to put the spindle assembly back together and give it a try with a real helical gear setup. So stay tuned for that, I guess.